realistically nothing more than, let me get the book definition if it actually gives me one, a collection of elements. A collection of elements. For example, if I threw out here the set of your ages here, age is equal, and the way we show a set is we do this, my favorite of all mathematical symbols. We put them in braces. Probably not your favorite thing if you're aware of braces, but okay. If I was just making a collection of the set of your ages, they would be, I'm guessing, anybody 12? We got some 12s. Anybody 13? We got some 13s. And if Rockwell was here, maybe we'd have a 14 or whatever. But right now, let's just go 12 and 13s. And that's all it is. These 12 and 13 are the elements in that set. Now, there's a couple things I suppose we need to talk about here. And they are the sets and the subsets of the numbers that we talked about. Let's make sure we have this down. When we talk about numbers, we have, oh man, we did this before. Did I give you the little paper on this? Okay. We've got mostly everything we know are what are called real numbers. We really probably should start with the very littlest and work our way up. Let's do that. Let's start with the bottom and work our way up. Let's start with the bottom of the tree. The bottom of the tree are what we call the, where are they there? Yeah, the counting or the natural numbers. Okay, and we can put those, and I'll put set notation in here. Ooh, I can actually get it wrong. The counting and the natural numbers are, when your parents taught you to count, they did the old 1, 2, 3, and so on, and so on, and so on. Okay? They didn't start you at 0, because if they did start you at 0, they started you at 0, then they would have given you the whole numbers. Okay? Whole numbers are exactly the same as the counting numbers, except you add the number 0. Why we do this, I don't know, but notice what we're missing here. We don't have any negative numbers. We don't have any fractions. We don't have any square root signs. It's all nice and neat. Okay? Life was good back then, people, before we added all sorts of other things in there. Okay, and as you got into about end of 6th grade, beginning of 7th grade, we threw in there, well, we did throw fractions and stuff in there, but we also threw in there what we call the integers. What are the integers and how are they different than the whole and counting numbers? What did we do with the integers? We added negative numbers, but they're still all whole numbers. So we start with all the negatives going this way, maybe -2, -1, 0, 1, 2, and going forever in that direction. Okay, and then, children, scooch this up a little bit. With the, above the integers, we have the rational numbers, and that's where we start adding the fractions and the decimals. Okay, rats. Rational numbers. By the way, the word rational should make you think about what? Numbers that make sense. These are all the numbers that still make sense to us, and they are all the positives, all the negatives, and all the fractions, and all the decimals. So I'm just going to write the word decimal, fraction. That's what we added to it, decimals and fractions. Okay? And then we talk about the real numbers. What can you think of that we've dealt with so far this year that doesn't fit into these categories? Okay? Well, unfortunately, Unfortunately here with, well, I guess so. Okay, what's it say in your little thing? I want to make sure I get this the same as you. Yeah. Unfortunately, along with the rational numbers, we have what are irrational numbers, which numbers that don't make sense, and that's where we're going with that thing there, which are, Lauren said, high. Vicky Kala?
Square roots.
Well, not square roots per se, but square roots that don't work out evenly. Yeah. The square root of 3, there is no exact thing. The square root of 2, there's no exact thing. The square root of 5. Any square root that doesn't work out is irrational. Why? Because it ends up being a non-repeating, non-ending decimal. Okay? All repeating decimals are rational because all repeating decimals in some way are a fraction. Okay? For example, if I asked you 0.1 repeater, whether it is rational or irrational, it is rational because 0.1 repeater is the decimal equivalent of the fraction 1/9. And if they're repeaters and if they end, they're always rational. Okay, if they're repeaters and if they're non-repeating and don't end, let's write that down. It gets a little confusing. Non-repeating, non-ending decimals are irrational. And that again is all these. This pi, if you do it out, it doesn't ever repeat and it never ends. If you do the square root of 2, if I were to pull up, I think I did this before for you. If I take out, no, I don't want this. Sorry. I want to go away. I want the calculator. If I take my handy dandy little calculator and I go even the square root of 6, it's going to be a decimal. It only gives me, it won't go any farther than that. But that you can see, you look in there, there's no repeating involved in that at all. And it doesn't end, it ends there because that's all the digits the little calculator has on it. But it would never end. Okay? So those are all the sets of the numbers. And then with real numbers, believe it or not, we do have, and I'll just throw this out at you, don't think too hard about it. We do have, opposite of the real numbers on a whole separate category, we do have what's called imaginary numbers. Just food for thought. Imaginary numbers are, ladies and gentlemen, imaginary numbers are, nope, imaginary numbers are,
like a trillion and all that.
no, that's real. You can get a quadrillion. You can get any number, you can get any digits afterwards. Nick? No, Google's or even, those are all real numbers. Nope, it's this right here. The square root of a negative 16 isn't 4, because remember what square root is. Square root is the same number times itself. Tell me what number I would multiply by itself to give me a negative 16. It can't, because two negatives will always give you a positive, and two positive always give you a positive. So imaginary numbers are negative square roots. Now in upper level math, you will use this, and it does come up. But right now in 7th grade math, it will never, for your sake. But just know there are imaginary numbers out there that go opposite of the real numbers. Huh? Well, they come up with the letter. They call it the letter I. I is the square root of negative 1. And what that is, I don't know, but I don't need to know. So we'll just move on. Just so you know that's out there. Nick? A little I thing? If you got to somewhere where it was a square root of that, well, other than it saying you can't do it.
Yeah, you're one of those. Yeah,
Those big graphing guys.
It's like, whoa.
Lucky you. Brandon, please. Now, with these things here, they give you some symbols so that you don't have to write those words all the time, and they're in the book, but I'll write them here for you. Instead of writing the word real numbers, here is the mathematical symbol. It's the letter R with this little thing in here. That is the same thing as when you're talking about real numbers, you just put that letter R there. that looks like that. Put the little double post on it because that's what makes it a letter R there. You could actually do this too. You really want to get highfalutin. Okay, real numbers are like that. Integers are the letter Z. This is just a symbol that stands for the integers. It looks like this, and then they double up. I think they double them all up. Just so that you know that it stands for. That stands for integers. Rational numbers is the letter Q. And again, put a little double line like that so you know it's the letter Q. And is that all? Natural or counting numbers is the letter N. Again, with a double little post on it like this. Because they're going to ask you to list some sets and intersections and subsets. Okay. Got that?
Sure.
So we got more talking to do here. This little symbol, when you talk about sets, it looks like the letter C, but it's not. It's kind of a U-turn, whatever, means subset. This all gets really kind of confusing, but it's not so bad. For example, if I go back to this, we go back to screen here, okay, everything underneath something is a subset of it, okay? So here would be a way I could use that little symbol. Counting numbers are a subset of the integers. Oops, I guess that's not the exact way, but that's just kind of how you would say it. A is a subset of B. Private rectangles are a subset of B. What else can they say? And then we've got this little symbol. When it's an upside down U like that, this is called an intersection. Did we do this in intersections before? Probably not. And, well, intersections, when you see intersections, just know that that is things that they have in common. And then a U like this is called a union. And that means putting together. And I'll try to explain it as best I can with what little time I have left here. Oh, I guess they did some sort of a chart over here. So, for example, let me show you this. Here's an example. I'm going to shrink this down so I have a little room to work. Let's say you've got this. Set A equals 1, 2, 3, and 4. Set B equals 2, 4, 6, and 8. A couple questions we might ask here is this. What is this? A, boom, B, and what is this? Give you a chance to write that down, then be able to talk. Got that written down?
Yes.
Okay, first one. This says, what is the intersection of, what is the set of the intersection of set A and set B? In other words, what do set A and B have in common? What are the ones that they both have? What is their intersection? In which case you designate the set, and you would say, Nikki Kala, they have?
2 and 4.
Correct. The intersection of sets A and B are 2 and 4. The union of sets A and B just means you put them all together. In other words, you put all of the elements of the set. So you don't have to repeat the number 2, but it would be 1, 2, 3, 4, 6, and 8. It's combining, really it's combining both sets. That is the union of it, putting them together. Okay? And then they talk about a Venn diagram. I think you've probably done a few Venn diagrams in your life. Okay? Let's say this circle represents A. This circle represents set B. If I were writing the Venn diagram, this place in the middle here is what? It's the intersection. The numbers that they both have together, you would write in here. The numbers that A has that B doesn't have, which would be what, 1 and 3, would go over here. And the numbers that B have that A doesn't have would be, what do they have? 6 and 8. But the place where they cross, or they come together, they intersect, is the intersection of it. Don't you feel just a little bit happier about things? Oh, so much more to go. Gosh. Maybe I'll take it. Oh, one more thing we have to do here. If you see this little symbol, a 0 with a big slash through it, it's called an empty set. It means it's a set that has no elements in it. Okay, something that doesn't have any elements. What's that? It would just be, if I wanted to give the set of numbers of kids here that were older than 15, there's no elements, so you'd put a big slash with a 0 to it, there's nothing. It just means there's nothing fits in that set. That's kind of the gist there. Let me do one more example from the book here. Use a Venn diagram. Let's do this. If A equals 1, 2, and 3, 1, 2, and 3, and we're going to get a little crazy on you here. B equals the letter N here with this little thing here that goes like this, which are what? What is it when you see that N? All counting numbers. Counting / number numbers. Draw a Venn diagram to show that. Venn diagram to show that. How would you do that? First of all, is there an intersection between the set A, 1, 2, 3, and all counting numbers?
Yes.
What do both of them have in common? What do they both have? Nick? 1, 2, and 3. So all of A is in B. So you have your big B circle here, right? You have your big B circle, and it is all the natural numbers. Where would the circle A be? Where would the circle that shows the set of numbers A, Emma Christ?
Put that 0 in
Nikki Gala?
inside it.
Yeah, the whole B. There are no numbers. I'm sorry, this should have been A. There are no numbers in A that are not in B. There's no numbers out here for that. So you put your numbers 1, 2, and 3 in here. That's your letter A. It all goes completely inside of all the natural numbers because there are no numbers in this one that wouldn't be in that one. So the whole circle is consumed by that. One more, just for fun. Do I have enough time? Sure. A equals 2, 4, and 6. And B equals 1, 3, 5. If you were drawing a Venn diagram of that, what would it look like?
2 separate triangles. Circles.
No triangles, but circles is good, Lucas. You've got A, which is just 2, 4, and 6. And then B, you've got 1, 3, and 5. I guess I probably should have put the letters inside. Now here's a question for you. The intersection of A and B would equal what?
0.
There you go. Since there is known members of that they have in common, that's that empty set symbol. So that's where that would come in if they ask you that. It's too much for me